Yes, I'm Max. I work at Quviq with John and Thomas. John, of course, you know. Thomas, you can get to know. This is joint work, of course, with Ulf, who you may know as the author of Agda, the Agda programming language, and Arnaud, who you should get to know, and me, who, well, you know. What's this about? It's about property-based testing, right? That means testing systems without writing tests for systems. That is a way of generating tests from as much understanding of the system as possible, or the specification of your system as possible, but without having to do any of the actual boring work of writing tests. Only the fun parts. Okay, so what does that mean specifically? Specifically, it means we're going to do three things. We're going to generate random programs, we're going to run them, and then we're going to check generate random inputs for our programs. We'll get to random programs. Programs, and check that the result of running the programs are okay. Okay, if they're not okay, what do? Well, we could either just report, well, I gave the program all this input, here's the error, or we could shrink the error, get a small counterexample, shows us exactly what's wrong with our program. That's what we're going to do. And then if the program succeeds with the random input, right, the checks all pass, we run the program again, and again, and again. And we do this overnight. We run millions of tests, all meaningful tests. Right? That's the idea. What's the degenerate use case for this? Well, it's checking something like this. Checking that the reverse and the append functions interact correctly. Is to say that if I reverse the append of x's and y's, I get the reverse of x's appended with the reverse of y's. Which, of course, you'll notice is not true. Right? And when we run QuickCheck, which is the tool that John wrote, I don't know how many decades ago, probably 6 by this point, we get a little counterexample, 2 decades, 3 decades, closer to 2. And we get a little counterexample that tells us this is the case for which your property is not true. Right? So if you try to take the reverse of 0, 1, you'll of course get 1, 0. If you reverse 0 and then reverse 1, and add them together, you get 0, 1. So they're not equal. Okay, so that's property-based testing. Right? And this seems almost naive. Right? How could this work? And it turns out it works well on a bunch of normal problems that you have when you develop software. Right? So many things behave like this, where we can take some program, run it on some input, treat this almost as a pure function, and then check some property of the output at the end. For example, encoder-decoder type things, when they're not generated from some metaprogramming thing, well, they have a round-trip property. There should be some form of relationship between decoding and encoded message. Likewise, data structures. If you have a tree, for example, supposed to be sorted, in order to traverse it, you should get out the sorted thing, right? This thing and many more similar properties of data structures are things that you can quick check. And finally, maybe the most interesting example of the pure functions is running a compiler. A compiler might not seem like a pure function, right? It might seem like a program that does a bunch of I/O and hits the file system and does blah, 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 but really, morally, a compiler is a pure program. It takes a program and spits out bytecode. That's what it does. How it does it, really not relevant, but it's a pure function, a pure program. So there are all these things we can do for pure-ish code, right? And the complexity here is just how do we generate random messages that are interesting? How do we generate random trees that are interesting or random programs that are interesting? And there's a lot to be said about that. This is not a talk about this. There are plenty of other talks on this topic. However, what this is a talk about is testing stateful systems. That is, systems where it's not as simple as just taking an input, running it, and producing an output and checking something. But there's an interaction. There are many things going on. And so the question is, how do we test a stateful system? And it's really two questions. What's the input to a stateful system? And 2, what do we actually want to know? What do we check of the stateful system. And the trick is, of course, we treat the stateful system almost like a compiler or an interpreter for its API. Right? We turn it into something that's like a pure program. So the input that we're going to generate is just a sequence of API calls. And the output that we're going to check is some correspondence to a model of the system. Okay, so we're going to abstract the system, we're going to generate some API calls, and we're going to check that the system corresponds in behavior to the model of the system. Okay, so I haven't practiced this slide, so you can read the bullet points, right? There are sort of 4 things we need to do. We need to abstract our actual state. We need to model the effect of API calls on the abstracted state, right? That is to say, when you change something in the API, does some change to some complicated big database? Well, if we can model that in our small abstraction. We need to generate sensible calls. That is to say, don't try to generate the first thing you do an add auction call to a user who hasn't registered on your auction site. And then there's this comparison to the model of your system. Okay, so this is a testing strategy. John has described it many times before. And what's new now is that we have a package library that lets you do this, right? So it lets you write all this nice model code and the nice generators in Haskell, which is a nice language for modeling things, and then lets you test code in any other language or in Haskell. All right. So I'm going to talk about what this library does, how we do it, and what's interesting about it. So we're going to go through some code. So I better be looking exactly at the code while I do it, otherwise I'm going to get lost. Okay. So remember, there were 2 parts to this, right? We have a model of the system, and we have the actual system. So let's first look at what we need to provide to get the model of the system, right? So there are 4 main things, let's say 4 main things. So in order to define a state model, what we need to do is we need to describe the actions of the system. That is to say, the API calls that we can make, but also perhaps things that are not purely API calls. We'll get to what those are in a moment. And then we need to talk about what's the state of the system, right? That's this type state here, this type variable. Say, okay, there's an initial state of the system when we start all our tests, and then we start performing some actions. Remember I said we had to generate sensible API calls. So there's a precondition which tells you for a given action in a given state, is this a sensible action to take? And then there's this little function here called nextState that takes a state, an action, and a var a, and we'll get in a moment to what those are, and produces a new state. Okay. So the nice thing here is, of course, we have a model, we have an action, produces some form of result, we can update our model, but there's a problem. All of this is not at runtime, right? We're modeling the system. So if I have an action that's supposed to produce an HTTP response, right? I make some API call and I'm supposed to get back some record of some sort. That's the type A, result of an action. That's not available when I generate my API calls. You saw there were 2 stacks, generate all the API calls, run it. So what I have to do is I have to say, keep the result of this action around for later, but don't inspect it. So that's just a variable A. You can think of it as a symbolic value of type A. And then there's some stuff you have to do to create an arbitrary action and shrink them and so on that we won't get into in this talk. Okay, so that's the run side, or the model side. Now we'll get to the run side. So for running, what do I need to do? Well, I need to be able to say, perform this action in this state. That is to say, this action in this state turns into something of this result in some monad m, that is to say, somewhere where I can run my API. So maybe that's, a reader monad with a little address or whatever, or it's something with a little bit of mocking in it, or something like this. And then there's a post condition, and we'll get to what this env thing is here in a second. The post condition is a way of saying if I started in this state and I ended up in this other state. When I ran this action, and it produced this result, is that okay or not? Okay? So far, what we've said is, we have a way of running an action, and we have a way of checking, did it do what we expected, given our model? And then there's this end thing, which just tells you how you translate the things that you saved for later into the things that actually exist at runtime. And get into usage of that in a little bit. And note here, because we're parametric in M, the monad in which we run this, we could have multiple backends to consider, right? Like running locally, running distributed, running with some mocking, running with more mocking, running with IO sim, which is a cool little library that the people over at IOG wrote for mocking all of IO and simulating it. But we have a choice of backends, that's the important thing. Okay, so let's look at an example of this. Sorry I had to do so much setup, but now we'll get to look at a cool little example. So what we're going to model is the Erlang process registry. And of course, the Erlang process registry is in Erlang, and we're in Haskell. So the first thing I have to do is I have to implement the Erlang process registry in Haskell. Okay, but that's a simple thing to do. There are three operations: where is, register, and unregister. Where is lets me say, I have this name for a thread. Do you know which thread it is? Register lets me say, please associate this name with this thread. Right? The string is the name, the thread is the thread. Right? Then unregistered lets me say, I don't care about this name anymore. You can forget about it. Okay, so it's a simple little system. It has to work in a multi-threaded environment. It has to do the right thing and so on for some definition of the right thing. So it's a simple enough example that we can model. Okay, so let's start modeling it. A clear abstraction of this system is just pretending like we have a global map from names to thread IDs, right? But they're not really thread IDs because remember I am at generation time. First I generate and then I run. So really what I have is a map from names to variables representing thread IDs. And then I'm going to define my actions. What can I do? Well, I can do the things that were in the API, right? I can do where is, so I get a name, and it returns to me maybe a thread ID. I can register a thread ID, but again, we're generating this at generation time, so I need a variable there, and I can unregister a name. And of course, this is not very interesting, because as everyone knows, there are no thread IDs just floating around in the universe. The universe doesn't contain threads. So I need to create those somehow. I need to do what you'd call test setup, right? So I can add another little action that's not part of the API, but that's part of my tests, where I create a new thread that goes away and does something. Maybe it just sleeps, maybe it interacts with other threads. You know, that's your choice from modeling. Okay. Then the next thing I need to do is I need to say, how do these threads interact with my state? Right? So I have three actions that really interact with the state, or two actions that interact with the state, I should say. That's registering and unregistering. So when I register, I say, okay, put the name in the map. And when I unregister, I just say, delete the name from the map. Of course, you'll notice, if you're really, really keen-eyed, that I'm using the monoidal mapend here. This is a non-overwriting write. So if we have the old name, we keep it. That's just how the Erlang process registry works. Okay. You'll note, of course, this thing differs if you know Erlang from the Erlang process registry, where if you try to unregister a name that doesn't exist, it will crash. We don't model that here. I've just ignored it for this presentation. Okay, so that's the model side. Then there's the run side. And the run side here is really straightforward, right? It's two things. I need to say, how do I run the things in this test, right, in this environment that I'm testing? And what does it mean for it to be correct for this particular system that I'm testing? So in our example, running the actions is straightforward. I mean, you know, register is register, where is where is, spawn is just spawn some thread, whatever. We don't need to care about those. The interesting thing is the post condition. Because this is really what says my system is behaving correctly. Because what are the things I can observe about my system? I can ask, where did you map this thread to? Right? It's sort of an extensional kind of property that we're testing. We're just asking, does it do the thing I expect it to do? I'm not looking into the state of my system. I don't care about what the implementation of my system is here. I'm just asking it, did you produce a result that makes sense with my model? Specifically, if I ask for a name and I get some particular result, it had better be the same result as I would have in my model state. Right? So if I've mapped something in the model state, I better get the same thing out when I run this action. So, anything else to say about this? Clear as mud. Okay, so we run it. QuickCheck gives us a nice way to run these models. There's a little bit more faff involved in reality, but it's basically this simple. We run it, and QuickCheck gives us a failure, telling us we weren't clever enough and we're wrong about how our system works. Specifically, it gives us this little script that we can use as a unit test that tells us where our post condition failed. So let's look at what we tried to do. First, we spawned a thread, var1. We registered it to A, right, the name A. Then we registered it to the name B, and we asked, what's at B? Right? And remember, our model is straightforward. It says, well, if you register it with a new name, it appears with a new name. And B did not return the same thing. Or where is B did not return the same thing. Clearly. I could have wished for nicer error messages here. You can put those in if you really want to. Anyway, so here's the natural thing to do. Update your model. Right? So the system has told you that your understanding of your system, QuickCheck told you that the understanding of your system is wrong. So you have to update your model. Said, okay, apparently I'm not allowed to register threads to two different names. Who knew? Well, I didn't. Well, I did, but you didn't. So anyway, we add that little check there. Say the register obviously only works if we don't have the thread ID in the existing registry. Okay, fine. That's a property for the system to have. And when we run QuickCheck now, it goes back and says, I ran it with 100 times with a bunch of different sequences of API calls, and now everything is fine. And of course, you can run it overnight, or you can do whatever you want. Okay, so that's all nice. What about harder things? What about testing that my system actually behaves correctly over time? Because there's one thing to say, oh, well, if my actions always return the right thing. But the interesting thing is to say, can I always make my system do something interesting? So there's a class of properties called liveness properties. And if you want to argue with me about the precise definition of the word liveness property, don't. I'm not interested. Go read a textbook. And then argue with me. And I'm not interested. Go read another textbook. And then argue with me, and I'm still not interested. I was never interested, but I got you to waste your time reading textbooks. Anyway, so for the purposes of this talk, a liveness property is something like, it's always the case that my system will eventually do something I want. Okay? So, Baby's first liveness property is like the server always eventually responds to all requests. Right? It might not respond straight away because it might be busy, but it will always eventually get to you. Or there's always some sequence of API calls that will unregister a given user from your website. Now, note, that might not be unregistered this user from my website, the REST call. Why not? Because what if you have an auction site, for example, you're auctioning off antiques, and the user has an open auction, they've been paid, but they haven't sent the goods out, maybe you don't want the user to be able to just delete their account and disappear. Maybe that's a facetious example, but you get my point. Okay, and an example that's very close to the hearts of the people who we did this work with is IOG, a blockchain company, is it's always possible for participants in a smart contract to get their money out, eventually, right? Money is never locked indefinitely in a smart contract, or value, or tokens, or whatever word you want to use other than money. Anyway, so what liveness properties are a way of talking about traversals of the state space, right? You walk around the state space, there's always something good that can happen. So what we're going to do when we test them is precisely this. We're going to walk around the state space, taking blue little footsteps around the state space. This corresponds to the always. Take some random walk in the state space by just issuing API calls, and then say at some point, we have a goal, something good eventually is going to happen, and the eventually is going to happen by you, the person doing the modeling of your system, writing down a strategy that lets you reach the goal. These are the yellow footsteps. Okay. So let's look at an example of this for the registry. So the property that we're going to be interested in is the programmer can always register any thread under any name without breaking the system. Okay? So what we're going to do is QuickCheck Dynamic gives us this little way of writing scripts for our tests that says, pick any actions, right? Run any bunch of actions in the system, and we can say, pick a random thread ID and pick a random name, then run some strategy, strat, that is defined up here, and we'll get to what that is, to get you to a goal state in which looking up a particular thread ID in the model will be the same as just returning the name. And then run any random bunch of actions. So what are the parts here, right? It's always possible, that is to say the any actions, it's always possible to register any thread under any name, that is, it's always possible to do something, strat, under which the end result of that is the right thread is registered under the right name without breaking the system, that is, we can continue running afterwards. Okay. Now, what's thread? Strat. Strat is something that the user provides. This is your yellow footsteps, your strategy for saying, here is why I believe this property to be true. And in this case, it's just a higher order function, takes the thread ID, takes the string, right? So the thread ID that we want to register, the string or the name we want to register it under, and gives me a script of actions to run to reach the desired goal state. Okay, so let's try. Let's try writing down the strategies to reach our goal. So the obvious one, right, is I'm supposed to register the thread ID under the name. So I register the thread ID under the name. And I run QuickCheck and it doesn't work. Okay. Well, it wouldn't be an interesting example if it worked. So what happens? What happens is we spawn two threads, var2 and var3, right? We register var3 under the name A, and then we say, pick the random values, and this is what this for all Q ugly syntax means, that I didn't have time to hide and pretend is much prettier before this talk. Pick a random A, and pick the thread 2, and then run the strategy on those. And you'll see, we've already registered var3 under A. Here we try to register var2 under A, and that doesn't work, so our assertion fails. Okay, Clearly, the problem here is that we are not allowed to overwrite existing names. Okay, easy enough. I change my strategy, unregister the name first, and then register the thread ID under the new name. Is that going to work? Is it? Why not? What happens if it's not registered? Only in Erlang. Concurrency. We haven't spoken about concurrency. We're not doing concurrency here. Okay, so you see, I'm being unfair. I've only shown you, code really quickly. I've given you a bunch of examples, but in reality, you don't have much more context than I had the first time I poked around with this, right? Because I really thought this was going to be enough. Okay, I unregister the name so that I can overwrite it, and then, boom, I run into exactly the same bug that I fixed earlier in the model. Right? So you'd have thought that I would have been smart enough to... No, I didn't remember. So what happens here? Well, this time we only need one thread. So QuickCheck tells us, I spawn one thread, I register it under the name A, and then I pick for you to try to register it under the name D. Okay, so you try to unregister D. Okay, D is not registered, but this is not Erlang, so it doesn't crash. Then we register var, the thread, right, under the name D, and it doesn't work. Why doesn't it work? Well, because I can only register one thread once, right? This fix that I did in the model. Okay, so now QuickCheck has told me this twice, so now maybe I remember it. So anyway, I refine my model or my strategy a little bit more. I take the model state, I look up the thread ID, and I unregister the name that it's registered under, if there is such a name, and then I unregister the name I intend to register under, and then I register. And now I run QuickCheck, and it works. Okay. So, in other words, I started with the goal, I want to show that my system always behaves in this predictable way of I can always register threads. And what did I end up with? Well, I ended up being told twice that I'm an idiot, right? And being told, here is the reason why that doesn't work as simply as you think, right? And now we're fortunate that in this system it does work. A lot of the time when you're doing this stuff, what you end up doing is bashing your head against it for a while, and then you realize, oh no, the property is not true, and you have to go and fix your system, right? But QuickCheck guided me along the way. And the amazing thing that you might not appreciate, if you're just seeing it the way that we're looking at it now, is that I told QuickCheck, here is the API. I gave it a way of generating random things, and that's a really naive way. I just pick a random string and pick a random this, that, and I put the API together. And QuickCheck came up with teeny tiny reasons why I'm wrong about my system. Okay, really the smallest possible counterexample that tells me why what I thought was true about my system isn't true. And that's shrinking. And that's a really powerful thing. Unfortunately, we don't have time to go into the details of how that works in this talk. I think we don't have slides for it, so it doesn't matter. See, I almost timed this talk out perfectly. Anyway, so what did we learn? Well, so 3 bullet point slides. I can just read you the bullet points so you can read them. The point is, it's fun to do this stuff because I get told by the computer when I'm making a mistake, right? I run QuickCheck, it immediately comes back with a reason why I'm wrong, and I can change what I'm doing a little bit. Okay. It's straightforward, right, in the sense that we had an API. I translated the API to some representation. I abstracted a little bit in a way that sort of seemed reasonable, and then I modeled my system and ran it. What's the third thing? Might be true. Anyway, the point is, you have readable code. You can read it, you can run it, it documents itself, and that's it. And just to convince you that I'm not selling snake oil, here are some of the places where you can use this and where we have used this and similar technology, right? So if you ever, for some reason, make a transaction on the Cardano blockchain, yes, that's us. If you ever answer the phone in the free part of the world, yes, that's us. If you ever see a Volvo car driving down the street, not stopped, I mean, it's probably not us, but yes, it's us. If you ever get your web request to answer in more than 4 seconds, right, that's us. If you're sick in the UK, that's us. Or, well, yeah. Well, anyway, there are lots of other examples. This stuff really works, right? It's neat, and you can really make it work. And we have made it work. And that's it, I think. I think that's all I have to say. How much time did I go over? I didn't go over by anything. Amazing. Okay, please, come talk to us.
Thank you, Max, for your talk. Are there any questions? Okay, I see hands.
Thank you. That's been impressive and inspiring. Have you considered integration with effect systems? So whenever you have a effect monad like polysemy or effectful, you have something very similar to the actions, right? So you've got your ADTs for all the API calls. So have you considered, do you maybe know the answer to the question whether we can have a generic integration with a particular effect system?
Probably, I think is the answer. We haven't done it. I worked with some code bases that use these freer and freer simple things and so on. And I mean, they're relatively straightforward to manipulate, right? People don't usually do crazy stuff in there. You do it completely generically, I don't know. So the problem, of course, is this distinction between runtime types and model time types. And that's I didn't tell you why there is this distinction in the talk, but the distinction exists because otherwise you can't do shrinking, and without shrinking, random testing is completely useless. So the tricky thing there is identifying which types can I only get a hold of at runtime, and which types does it make sense for me to generate results for or generate random values for at generation time.
Mm-hmm. I see. So I was thinking of testing the application in a way where all state changes are only expressed via application's API. So I see your point that this pawn is kind of out of band, out of application usage. Yeah, and of course we would have to provide the precondition, postcondition as well. But still, maybe there's something to look at there. Thank you.
And again, this stuff is available on Hackish, right? So, like, if you want to do anything like that, it should be relatively straightforward to build on top of what we've just seen here to try that out, right? That I don't think doing that nicely should require any amount of integration here. But I might be wrong, and if I am, come talk to us.
I've seen examples of people verifying their design, especially covering liveness properties with things like TLA+, but that's just the design and not the implementation, whereas this is the implementation. So would you say that this approach obviates the need for something like TLA+?
Does anyone in here actually like TLA+? No, exactly. So yes, right? No, I don't like TLA+. You can't read TLA+ specifications. They're completely, it's impossible. That's my personal opinion, right? Yeah. So there are variants of this in our Erlang QuickCheck that can handle that. We haven't integrated that into the Haskell version. For TLA plus, the slightly more serious answer is that there are tools around TLA plus, right, that we don't have here yet. So, I would be, TLA plus is whatever, the, 10,000 BC technology that people have been working on since, before the dinosaurs. And there's a lot of tooling there. We're probably never getting rid of TLA plus, right? But what this can do is help you at the next stage, right? Where you've actually got an implementation. So it's very difficult to take those models and relate them to implementation. Right? So that's maybe where I would say it's a better place for you to step in with this kind of tool. We've got a question up there, and then we've got John, whom I'm not sure is going to ask a question.
So you might have just answered the question I had, but are there any significant differences between this Haskell version of QuickCheck and the Erlang one, specifically with regard to testing stateful systems? So
this stuff has been around in Erlang QuickCheck for a long time. I think it's almost better to let John answer this question, but this, these ideas, we've had them for a long time in Erlang QuickCheck. There's a lot of stuff there that's not in here, but there's also some stuff in here that's not in there, right? So these scripts that we looked at, there's actually a whole universe of complexity behind making that work nicely, and that stuff is not in Erlang QuickCheck, right? We're going to put it there when we have a good reason to, I hope. But so there are differences, right? The best thing to do is, if you want to run Erlang QuickCheck, buy Erlang QuickCheck. I can say that because we sell Erlang QuickCheck, right? John's more of a comment than a question, I think.
Yes, I was just going to make a comment. Can you hear me? Yes. I was going to make a comment about the concurrency testing, because that is one of the things that is part of Erlang QuickCheck.
Yeah.
So the trouble with testing concurrent programs is what properties are you going to test, right? And TLA plus is very expressive, but it makes me tear my hair out. But one very simple property is linearizability. So you're testing that something behaves atomically, even if it's not implemented atomically. And a very high proportion of operations in concurrent APIs are supposed to behave atomically. It's something like 70%. So we have an automated property that says these operations are linearizable. And the great thing about that is that you can just use the sequential state machine spec and say, oh, by the way, I want to test concurrent programs instead and test for linearizability. And that lets you test for race conditions with a 2-line change to the code. And we found some very fun race conditions in databases with that. That was my comment.
It may be something to say about liveness properties and eventual consistency, but we haven't thought that through, I think, yet. I'm not sure we have an answer. But there's a lot there. There's a lot that one could do, and there's a lot that QuickCheck can do.
Okay, I see no more. Oh, another raised hand.
So I was thinking about one of the first talks yesterday about stochastic sources of failure, for example. So whether it would be possible also to consider that in your model, that maybe you have to do like some random walk in the state space or something in order to model some stochastic effects.
So if your system behaves randomly on purpose.
No, like for example, if it could be a random failure that prevents you from talking to a server or something like that.
Right.
So it's not on purpose, but.
Right. So so there are many things you could mean, right? So you could either mean I live with random failures. So my system has to be robust to random failures, right? And then you would put in the action that models random failure, right? And we've used that in some places, right? So you say, okay, we model random failure, and then of course you can, if you're clever enough, you find a way to instrument the API code that you're calling, so that when you've modeled your random failure, you either really cause that server to fail, or you pretend there's a network partition or something. That's one thing you could do, right? So you can model it as part of your model. If you have explicit randomness in your system, of course, you'd have to abstract that randomness in your model. So that's a different source of randomness. So for what you're interested in there, I would explicitly model these kind of things. And we have there is some version of this for some domain where we extended it to model crashing systems and so on. Right, that's a generic thing, but it's definitely doable.
Okay.
When you are testing systems written in languages other than Haskell, then you have to run them as a separate process. And does this system somehow handle that, or are you supposed to just set it up separately? And also, do you restart the system between the tests, because it's sometimes considered, when you have a stateful system, then tests can interact in such a way that maybe you are testing properties such that they shouldn't break, even if you are, which I think might be the case, but still I wanted to make sure.
Yeah. So the answer is it depends and it depends, right? So one of the reasons why in the model we had, there is this, I can go back for 1,000 slides, right? One of the reasons there's a spawn action here, right, is because you explicitly maybe don't want to test with previous things, right? And now spawn is a silly example, but in a lot of models like this, there's an init action, right? A setup action that does your test setup, right? So that at least reflects it into the world in which you're working, right? So then you get to choose, how much setup do I do? Right, so maybe I just look in whatever some log file or something. Is the system running, right? And did it crash or not, or whatever? And maybe I don't restart, or maybe I do restart, right? And that's a choice you have here. But it is your choice, right? And of course, because you can run this stuff in I/O and so on, right? You get to do this instrumentation at least as part of sort of reasonable Haskell code that pokes at the OS or calls out to whatever external setup, testing tool or whatever, Kubernetes nonsense or whatever you want to use, right, to run your tests.